Next, we have Matthew Calder, who is an intermediate developer and a fellow math group member. He will show us how to make numerical computations in Maple even faster. Welcome, Matt.
So my talk is on numeric computations and how you can make them faster. So Maple has the capability to do arbitrary precision computations, numeric computations. That's one of its most powerful features, right? So you can set digits to whatever you want. So default is 10. So this is the environment variable here.
Again.
Where's it going?
Matt, can you just increase the font size so we can see a little bit better? Thank you.
Is that good? Okay. I'm going to do it down here just so it's in. Okay. So with digits, you have so default 10, but you can set it to whatever you want. So if you want, I just set it there to 10 already. That's the default. 10 is the default. You can set it to 50 if you want. You can set it to anything you want. So there's a kernel ops max digits. Just some very large number. So this is the highest you can set digits to. So I wanted to show this one example where, just to highlight that it's not necessarily you want to go to hardware floats. If you have a good algorithm, a quick algorithm, software floats are the way to go. So for example, here, so this is a code I have for the Gauss-Legendre algorithm for approximating pi. Okay. It's very quick. So if I just do do 5 iterations, and I'm going to set digits to be, I'm going to close that, get out of the way. Let's say 200 digits. Get that, so I'm going to assign that quickly, and then compare that with pi. So I'm going to use 200. So when you do the square brackets, that just means you're telling eval_f to use 200 digits working precision. So p minus what pi is. And you can see it's very quick after just 5 iterations. So you don't need to worry about like hardware floats because you couldn't even get that much accuracy in the first place. All right, so 84 digits of correct digits. Pi, I think it's hard-coded the first 10,000 digits of pi in Maple. So it's not actually doing any computation when you're evaluating pi. Beyond that, though, it might have to do computations. So moving on to hardware floats. So with hardware floats, so that's 64-bit floats or double precision. So that uses 15 digits of accuracy. So if that's all you need, that's great. So there's packages like linear algebra, which will automatically use hardware floats if necessary or if possible. So for example, if digits is 14, so that's one less than hardware float digits, you matrix addition, it's going to automatically convert it to float 8. So the first two matrices were type anything, and the third one, the sum, was float 8. But if I were to set digits to 16 and do the exact same thing again, it's going to use S float. So now it's switching to software floats when it's larger than 15. I'm going to set that back to 10. So the eval_hf command. So if you wanted to use hardware floats, which are much quicker, you can use the eval_hf command, which uses a different interpreter for numeric computations. It's less overhead, has faster speed. It's like the express lane. So as long as you're not doing anything too complicated in terms of Maple structures and commands, you can use that. So there's a list here in the link of the commands that you can call. So basically simple, arithmetic operators and basic functions like trig functions. So you can use that. Right, so that one big limitation, of course, is that what you can use is limited, but when you can do it, it's great. So let's look at this one here, this command double values. So you're going to pass it a float8 vector. I'm specifying the size, and all it does is go through all the elements and double them. So it doesn't do anything fancy. So it's going to generate a random vector here. I'm going to create copies of it just so I can compare it with other things. So 1,000,000 elements. So if you just do it blindly without, in regular mode, without LHF, it'll take about 980 milliseconds. But if you use a val-HF mode, about 56 milliseconds, which is a substantial improvement. So the rule of thumb is it's about 10 times faster if you do things in a val-HF than within regular numeric computations. I'll mention here that so you passed the vector, and it's going to double them in place. You're not actually creating a new vector. You're not allocating any new memory. You're just doing everything in place. And I did pass the size here, but I think 1 or 2 releases ago we added the ability to use num-LMs within the val-HF, so you wouldn't need to do that. The reason I did that is because in compiled mode, which what we're getting to now, you would actually have to pass the size. So this command, like double values, can be compiled with a compiler compile. It's using a C++ compiler. So let's compile that. There's going to be some time required to do that. So it took about 141 milliseconds of CPU time just to compile it, but that's a one-time thing. Because if you were to call it on the C copy of that vector, 2 milliseconds. So that's compared to 56 milliseconds with a val-HF. So that's about 30 times faster. And the rule of thumb is another factor of 10. So regular to val-HF, factor of 10, val-HF to compiled, that's factor of 100. Or a factor of 10, and from regular to compiled is a factor of 100. And as you can see here, so I printed it for a reason. You can actually see the literal call to define external. So it saved a DLL on my computer right here. And so if you were just to call define external like that, you can just do it that way without having to recompile it in a separate session. Right, and those things can be picked off with using the op command. So the command name and the DLL. So I'm going to do a couple of applications here. How am I doing on time, Kashka?
You still have 3 minutes. You're good.
Okay. So 2 examples here. So I'm going to do a numerical solution to an ODE. So we have this 3-dimensional system niche value problem. First, we have the dsolve command, which can do numeric as well as symbolic. And you can also compile it. So you can see here that this is built in fundamentally. So I'm going to compile it. I did a little trick here with typefunc, which maybe Eric will be talking about in his talk next. Types. So it generates a procedure to evaluate the solution numerically. At any point, you pass it. You can do an ODE plot, and you get this. So what we're going to do here, I'm going to load a file I have. I'm going to show it to you quickly. Numeric solution here. So I just have this procedure which takes the parameters like the initial time and the initial y value and the time step and the size, and you also pass it a vector. So it's going to do an RK4 loop on the 3 components and store them in data. And then when you're done with that, back to Maple, it's going to store it in this data array and compute it. So I had this auto compile option, so I'll mention that. It's option auto compile. So what that does behind the scenes is it calls compiler compile the first time you call it, and then from that point forward, it's going to replace it, and it's going to use the compiled version. So if I had to do this again, right, 6 milliseconds as opposed to 630 milliseconds, so it's really quick. So I'll do it there, and I can also plot it. So I populated this array, this 4-dimensional array. I guess 2-dimensional array with 4 columns. With what did I use? I think 100,000 sample points. And you can use data plot to plot it as well. So you can see this for a sanity check that this matches what we had with the there. Dsolve would use much more sophisticated stuff. Maybe Kashka or Alan can comment on that, but I know it does create an array and store the values. And I'm going to do a quick example here. So I have the logistic map. So that's Notepad again. So you have this recursion initial value in the parameter R, and you want to do the bifurcation diagram of it as you vary the R value. I'm going to load that. It generates the bifurcation diagram. So I'll show you quickly what I did there. Don't worry too much about these commands here, these first ones. So I use what's called applicable modules. Instead of a command, I define a module, which you can have local commands in it, but you have apply or module apply command, which is what's called when you call the command as if it were a regular procedure. Right, so I have some internal things just for type checking. I was being pedantic here. So what I'd like to do in like procedures where I do like this, numeric computations and have hardware floats. So you have a main command, so that's the module apply. So you do all the regular Maple stuff, but you dispatch to what I call a workhorse procedure. So the workhorse procedure is going to go through every R value, and for every R value, it's going to record which Z values are touched when you iterate. So it's doing some tallying. And down here in the module apply. So it does the workhorse. So you generate the array and do the workhorse to populate the array. One thing I'll mention, so I do normalize it so it's an image tool image. And to touch on something that Dave talked about. So here, instead of doing just map with X maps to 1 minus X, I did 2 separate calls to map with a val-hf in it. Because the asterisks and the plus sign, they're optimized for val-hf. So I call it val-hf and I do everything in place. So I'm not generating a new R table and populating it.
Matt, we're almost out of time here.
Okay, I think I'm done here. So I already showed the plot. So yeah, I guess exactly on time. I'll be happy to answer any questions.